So, Rose, today we're going to design a Laval nozzle in the resistor jet thruster based on some mission specifications. So, speaking of the basic structure of the nozzle, we can divide the nozzle into four parts: the heating chamber, the converging section, the throat, and the diverging section. When the propellant medium, the gas, flows through the chamber will heat the gas to a fine temperature and get it prepared for being compressed when it flows through the converging section and reaches the speed of sound when it flows through the throat. In this case, we may call it a choky flow, right? And get expanded when it flows through the diverging section and turns into supersonic speed and exit the nozzle. Some thermal properties of the propellant working medium, we may choose the nitrogen gas in this case, and the molecular mass M with a capital M is equal to 28 gram per mole, and the specific heat ratio gamma, the lowercase gamma, is equal to 1.4, and the universal gas constant, the R with the bar on the top, is equal to 8.3145 joule per mole dot Kelvin. And there are some operating condition and basic design has to be noticed. The first one is the total temperature of the heating chamber, which is P with a subscript 0 is equal to 0.2 metapascal, and the area expansion ratio epsilon is equal to 10. The indicators of the design is used to solve for our demanded thrust. The total mass of the thruster, the m with the lowercase m, is equal to 500 grams, and the systematic specific impulse, the I with the subscript sp, is equal to 500 seconds. The total velocity increment delta v is equal to 20 meters per second. All right, now next is our indicators for engineering. Maybe they're not our case, but I want you to pay attention to this operating temperature. This one is quite important. The T with the subscript 0, T0 for short, has to be less than 333.15 Kelvin. If our final solution of this design, this operating temperature, if we solve it to be greater than this 60 Celsius, it indicates that our design is failed. We have to redesign to adjust some parameters in our design. Whatever, let's just continue. So there are some expansion nodes here. The first one is the expansion ratios. There are three expansion ratios in this case. The first one is the area, the pressure, and the final is the temperature. And about this expansion, this pressure expansion ratio, it should be noted that there is a complete expansion assumption, which indicates that the exit of the pressure is equal to the ambient pressure P with the subscript A. This one is quite important in our design, right? So let's show some basic assumptions for our design. The first one is the complete expansion assumption, which is shown before, just before, and the one-dimensional flow, the isentropic, the steady flow, the compressible flow, the adiabatic, and the invisive flow. The dynamic indicators and geometry indicators is the parameters to be solved, other parameters to be solved. So the first part, the dynamic part, there are some indicators here, the demanding thrust, the F prime, maybe it's demanded rather than demanding, and the design thrust F, the correction factor lambda, the systematic total impulse, I total, and the expansion ratios, the 3 of the ratio. Maybe the 3 of the ratio is not so dynamic, right? All right. So the next one is the geometry indicators. This bunch of indicators may be so complicated here, so I'm going to show a sketch of the Laval nozzle. All of these geometry indicators will be shown above this nozzle. So you can just print a screen here, or I'll share this PDF in my video, in my NetDrive links. You can just click the links and download it in my comments. So let's solve for our first parameter, the zeta E. By definition of the pressure expansion ratio, the zeta E is equal to the P with the subscript E over the P with the subscript 0. This explanation I'll not repeat it again, but the value of the total pressure of the chamber is set already, is equal to 0.2 megapascal, which is important. So according to the supersonic flow theory, the pressure expansion ratio is defined by specific heat ratio gamma, the lowercase gamma, and the area expansion ratio epsilon. So let's just, this one is known to be 10, and this one is known to be 1.4. So we can solve zeta E by this complicated function, right? All right, its two value is also it's just shown above. So given the total pressure of the chamber of the nozzle, the P0, and the pressure expansion ratio zeta E, which is just solved in our case, we can get the ideal expression of the nozzle P subscript E, because it's ideal. So why is ideal? Why is ideal? Because the those those basic assumptions, they are all unattainable in our reality. So we have to introduce a correction factor lambda to just correct our demanded thrust F prime. And this one is for calculation the indicators, and this one is for designing our Laval nozzle. So this one is important, and this one will be used a little bit later. Now let's just move on. And by our complete expansion assumption in our design, this ambient pressure during the thrust operation is equal to the total pressure of the axial of the nozzle. So this one is important because it can be utilized to solve our coefficient of the thrust. So now let's introduce a coefficient, the capital gamma, corresponding to this lowercase gamma for our specific heat ratio, which is equal to 1.4. And by this definition, by this formula, we can solve for the capital gamma. And this capital gamma, this particular constant, will be used to solve for another dimensional thrust coefficient, the C with subscript F, and the ideal mass flow M with a dot on the top. So the systematic specific impulse y with the SP, total mass of the thruster M, the total velocity increment delta V are already given by the indicators for design, right? Those three parameters are all known. The working fluid is quite low in density, so that the loss of the mass of the thruster can be ignored. So we can assume this total mass is unchanged, it's constant, it remains constant. So by our momentum theorem, we can solve our demanded thrust, the F prime, and by empirically evaluate half angle, these three parameters, they're all empirical. They are empirical. Our converging section half angle alpha is equal to 45 degrees, and our diverging section half angle beta is equal to 11 degrees, and the correction factor for our thrust is equal to 1 plus cosine of beta over 2. And the relations between the F prime and the F prime is the demanded thrust, and the F is the design thrust. We will design our nozzle by this design thrust rather than this demanded thrust. This relations indicates that the design thrust has to be greater than our demanded thrust, right? So that it can meet our indicators. And by the design formula, thrust formula, which is 1.0 version, the design thrust is equal to the coefficient times the total temperature of the chamber and times the cross-section area of the throat. But we have just solved this one, right? And the beta is known, so the lambda is also known. And by the lambda and the demanded thrust, we can solve for this design thrust. So this one is known, and this total temperature is also known. So now let's figure out this coefficient. The coefficient gamma, the capital gamma, the specific ratio, the little gamma. Notice that the capital gamma is defined by the lowercase gamma, and the variables can be coupling. The exit pressure, PE, atmosphere pressure, or maybe it's ambient rather than atmosphere, because it's closely to a vacuum environment of the resistor jet thruster. The PA, the total temperature, the total pressure P nut of the chamber, and the areal expansion ratio epsilon joints determine the dimensional thrust coefficient CF by the following function. So this one is quite complicated, right? But we can just simplify our relations of this CF and this bunch of variables by our basic assumptions. So by our complete expansion assumption and our definition of the pressure expansion ratio, we can simplify our CF by this much easier function. So for this capital gamma is defined by our lowercase gamma. So this one is known, and this and this is defined by our zeta E, and PA is equal to PE, so this one is crossed out. And for this one is crossed out, so for the PA is equal to PE, so this one is crossed out. No matter how much this epsilon is, it doesn't matter at all, so this one is crossed out too. So our final parameters is left with the merely lowercase gamma and the zeta E. And the zeta E is known, right? The zeta E can be solved by our definition of the zeta, our definition of the our relations of the epsilon, zeta E, and gamma. Epsilon is known, the gamma is known, the lowercase gamma is known, so this zeta E is known, and our gamma is known also, so this CF can be solved out. So finally, by our design thrust from formula 1.0 version, this design thrust is known. This CF is just solved. And this total temperature is set to be 0.2 megapascal. So this cross-section area of the throat can be solved out, can be figured out. And by our definition of the epsilon is set to be 10, right? So this AE, the exit area, can be solved by this epsilon, and our solved AT, the cross-section area of the throat. And next is our diameters and the lengths. It should be noted that the length of the chamber and the diameters of the chamber, they are all empirical values. They are not calculated by any principle. They are just empirical. They are just based on our experiences. But the diameters of the throat and the diameters of the exit, they can be derived by our geometry relations, which is the area of the circle. And this LT and LE, we can just let me draw a not so intuitive graph to sketch. This one is alpha, and this one is beta. So this one is the dt over 2, and this one is the dE over 2. Maybe you can just look back on my sketch. I've just shown this PDF. Yeah, here, right? You can just calculate what does the lambda really means, and what does this LE and LT really means by this formula. This work is for you, audience. I am not going to derive these formulas here because it's waste of time. So now we can obtain our curvature radius, the curvature radii R1, R2, and R3 by this empirical formula. They are all defined by our diameter of the throat, diameter of the exit, and just of the two. So the core of our geometry design is the epsilon, which indicates the ratio between our exit area and our throat area, and the cross-section area of the throat. By these two, we can solve all the geometric design parameters. So here comes the question of the chamber. The total pressure P to subscript 0 is solved out. What about the total temperature? Right? We are just put forward some demands for the temperature. We indicate that this temperature has to be less than 333.15 Kelvin, which is 60 Celsius, right? But what exactly is the concrete value of this temperature? So we're going to figure out this one. It will be our continued tasks, our target to solve. So let's solve for our T0. So first one, we're going to introduce the gas constant R of the nitrogen. By definition, we can find out that this R, this constant, is defined by our universal constant over the molecular mass of the nitrogen. And solve for this. This one is known, this one is known. So this R, this constant, gas constant of the nitrogen, is also known. All right. So by invisible compressible ideal gas assumption, the capital gamma is known by our lowercase gamma. And this total pressure of the chamber is known to be 0.2 megapascal, and the cross-section area of the throat is solved in our geometry design, and the constant R is solved. It's just solved, and this T0 is to be solved, right? So we can define our mass flow, the m dot, to be the function of the variable T0. This one is important. This formula is important. And bioenergy equation for our adiabatic flow, the ideal, remember, is ideal. This one is also ideal, right? It's ideal, it's ideal. They are all ideal. They are all ideal. The ideal exit velocity v with the subscript e is equal to a function of the lowercase gamma, the gas constant R of the nitrogen, the total temperature of the chamber T0, and the zeta E, which is the pressure expansion ratio. And this one is known by our epsilon and the gamma, lowercase gamma. And this one is just solved, and this one is known to be 1.4. So the ideal exit velocity v with subscript e is also a function of the variable T0. Both of the m dot and the ve are independent functions of the variables T0, which is quite important. We can ignore this function for just for soon, because we will obtain this calculation, this complex calculation in our Simulink plane in our MATLAB laboratory, which can be intuitive for us, which is intuitive for us. So by our design of the thrust formula 2.0 version, our design thrust is solved before, and remember this formula, the exit area is known, right? The exit area can be known by our epsilon and AT, and AT is solved in our geometry design, and the PE is known, right? The PE is known by our P0, which is 0.2 meter Pascal, and our zeta E, which is the pressure expansion ratio, which is solved to be which is solved by our epsilon and gamma, a little gamma, and our ambient ratio and our ambient pressure by our complete expansion ratio, complete expansion assumption. The PA is equal to PE, so this one is crossed out. Only left with the merely m dot times the VE. And meanwhile, the m dot is the function of the t0, the v is also a function of the t0. So this whole design thrust is a function of the t0, right? So this one is very, very, very important because we already know the value of the design thrust. So by this function combines all these functions above, we can solve for T0, right? So we can solve for T0 and we get our total temperature T0 of the chamber, which will be obtained in our simulation. So eventually we take the soft mass flow m dot and our demanded thrust f prime into our 2.0 version formula to solve for our demanded exit velocity ve prime. So we just obtain this formula. We can just replace the design thrust F by our demanded thrust F prime, which is less than this design thrust F. And we can solve our exit velocity VE prime. This design idea is very important in our design of the astronautics, maybe some satellites, maybe some rockets, right? So whatever, we can just solve our demanded exit velocity, which is to be utilized to be our reference value in our simulations. So by isentropic flow assumption and the energy equation, the temperature expansion ratio CE is equal to a function of the lowercase gamma and the zeta e. The zeta e is solved by our epsilon and our oops, this epsilon is just quite naughty. The epsilon and the gamma, the lowercase gamma. Epsilon is equal to 10, the gamma is equal to 1.4, and the gamma is also known to be 1.4. So this CE can be solved. We solve for the exit temperature T with subscript E of the nozzle. And this exit temperature will be used to set up our working conditions in the CFD simulations later. So we can just solve this TE, right, by this definition of the CE. This one is known, this one is known. So what is the principle then? The whole calculation, the whole design of these parameters turns out to be a reverse design principle because we already know our demand indicators, the ISP, the specific impulse, the total mass of our thruster, the lowercase m, and the delta v. This one can be solved for our demanded thrust, and by our correction factor lambda, we turns it to be a greater thrust. The greater thrust is the design thrust, and this one is used for our design of the nozzle. And we are provided with the conditions, the P0, the gamma, the epsilon, and our fundamental assumption. The maybe the fundamentalist assumptions includes the complete expansion assumption and some one dimension, implicit, compressible, blah blah. And finally, we will conduct a CFD simulation to test our design temperature T0 by comparing the result of exit velocity VER with the demanding exit velocity VE prime, which is just solved here. If not ideal enough, we can just adjust our design temperature T0 or the correction factor lambda to better our results. Maybe this design process can be conducted by our PID controller. Well, it will be conducted later, but I'm not going to do this right now. And finally, our reverse design principle design means that when we design the working conditions by given indicators rather than set up working conditions to solve the indicators, it's the indicators are all given. It's all given. They are all given. But if it's not reverse design principle, it's maybe some linear design principle. We can just set up the working conditions to test our indicators, solve our indicators, but now we already know the indicators, so we need to reversely solve for our working conditions, which means it's reversed. In the next video, I'm going to show you how to do this 2D simulation in our Ansys Fluent. In this case, I'm going to do a 3D simulations, but the 3D simulation, if I'm going to show you the Mach diamond, maybe it will be too damageable for my laptop. My laptop cannot hold up so much so much calculations. So in this time, I'm going to do a 3D simulations, just for our Laval nozzle, rather than showing you the Mach diamond. All right, so let's exit our PDF and close it. Let's just save it, and let's just open our MATLAB, the math laboratory for short. The start of the MATLAB can be a little bit longer than we thought. Let's open our Simulink, this modular programming plane, and create a blank model. Let's just wait for a minute. All right, so let's expand it and do our calculations using the modular programming plane rather than our linear code-based programming plane. Just for our just for our intuition. It's not for others, it's just for our intuitions. All right. So let's look back on our PDF and prepared our working parameters. In our Simulink, there are how to start our programming. Then I'm going to show you. The first one is, if you're more familiar with the library browser, you can just open up library browser on the top of our Simulink, right? You can just search, type your keyword. Maybe it's constant. Oops, I need to change this. You can type constant, and you're searching for the constant, but it'll be a little bit slower. So I prefer to close that and just double click the blank area of the screen and type constant and enter it. And here will show our a constant module. Looking at this little triangle here, it means the output of this module. Maybe there is another triangles on the left of this module, which means the input correspondingly. So whatever, let's delete it. Let's say our molecular mass, the capital M. So let's just type our constant. Oops. And click this words here, and let's say it's molecular mass, and enter it to be 28 gram per mole, but we may use the ISO units, so we may say it's 28 times E3. This E3 means 28 times 10 to the negative 3 power. So I just expand it a little bit. And next constant is the specific heat ratio, which is the little gamma, the lowercase gamma. So we type the constant again. Or maybe we can just select this module and Control C, Control V, and copy it. Right? There are two ways of creating this constant. I prefer the typing method. So click this. Let's just click this word here, and let's say that is gamma. It's little gamma. Oops. Maybe we can add a unit to be more intuitive per mole, right? So gamma can be represented by our specific heat ratio, the little gamma. It's just a dimensionless coefficient, so it has no unit. Let's say it's 1.4, right? It's 1.4. The next one is the universal gas constant. So let's just double click again, and maybe you can save this double click motion. You can just type, right? You click and type, you click and type, and you will show a bar here, right? Click and type. So it's our universal gas constant. Oops, I just typed wrong. I need to create a constant here, and click this word works below, and enter universal gas constant. My vocabulary is a little bit poor, so maybe, oops, you can, when you misplace this word by, like me, you can just put your cursor in this word and drag it to your original place if you like. Universal constant R bar is equal to, oh sorry, its unit is joule per mole dot Kelvin. Joule per mole dot Kelvin. My vocabulary is a little bit poor in these issues, so if I mispronounce or misexpressed some typical issues, do point them out in my comment below. So let's say it's 8.33145, right? Let's expand this one to show the value. Right, it's 0.3145. And the operating condition of the basic design, the first one is the total temperature of the heating chamber. So let's say it's we can just drag our cursor and select these three constant module and enter and type and click the create subsystem and enter and type and click this word again, and let's say it's it's the thermal property. Thermal property is gas, which is nitrogen, and nitrogen, just nitrogen, right? And double click this subsystem. We can rename this output. Right? If we want to create this output modular, we can just click and type out, and will come our output. And I'll delete it. We don't need this output. And also click the words and rename it as the capital N and lowercase gamma. Rename it, and this is the R bar. Well, maybe for the gas constant of the nitrogen is defined by M and R bar. Maybe we'll define it later when we scroll our PDF to that page. We can just leave them out. So let's click here. Oops, it's a better habit to control save our models. Let's say it's I've already created a Laval calculation for loop based on this PDF, but it's a Chinese version. I'm going to create a English version for our practicing and calculation. So let's say it's calculation English version. All right. Do save our module when we finish this bunch of things, this bunch of issues. So let's leave them out and let's say what's next. So we need to create a total pressure of the heating chamber. So let's say it's constant again. When you double click this blank area, you type constant and just type enter, and this constant will show above. Oh no, let's just delete it. And let's say this total pressure. Or maybe we'll capitalize it. Total pressure of the chamber, which is P with the subscript 0, M Pascal, the megapascal for our units, which is 0.2. But for our identifies our unit, we mean type again, which means, well, let's say the value of the gain is 1E6, and rename this gain module to be M metapascal to Pascal, which means this value of this constant module, if I drag this triangle on the right side and drag it to connect the input of this gain module, it indicates that the output the output of this motivation is 0.2 times 1e6 times 10 to the 6th power. So let's say our output is the P0. So we no need to worry about the unit of this bunch of things, right? So next is our area expansion ratio. I prefer to put this area expansion ratio into our geometric subsystem. So let's create a subsystem of geometry right now. Let's type subsystem, so and enter it. And we can create a subsystem here. And let's rename this subsystem to be geometric design. Geometry design. So let's say constant, type constant, and say is our area expansion ratio. Well, maybe we can save this by space. Ratio epsilon. It don't have any units here. So let's just create it and drag. We deleted the module and drag this empty input to our constant. Let's say this ratio is equal to 10, and our output is our epsilon. So we can design our geometric here. And for the intuition, we can just drag this one and leave them out. And it's a better habit to enter to type in display module. We add a display module here, which will display the ratio, the value of this output, and say it's is AER epsilon. All right. So now let's run it. You can see it can display our value of this epsilon. So it's better habit to just do this, just to do this condition, do this operation. So let's say what's next. The next is the indicators for design. So let's create a subsystem 2. Let's say it's subsystem. We scroll our middle button of the mouse. We can just open it. If we want to find our location of these modules, we can drag the screen, drag this area. If you can see my cursor, all right, and scroll our middle bottom of the cursor of the mouse. We can just do this effect. So let's say it's indicators for our design. And let's just maybe drag the vertices of this subsystem and just expand it. And let's double click this subsystem and enter it. And let's say our total mass of the thruster is m equal to 500 grams. So let's double click our area and type constant and enter it. And let's say it's total mass of the thruster, which is lowercase m. It's gram units. And let's say it's 500. And again, let's double click and enter gain and create a gain module. And let's say it's G2kg. And let's say is 1e -3, which means the 10 to the -3 power, and connect our output of this constant to the input of this gain module. And let's say our output is m. It's just m, and let's delete our input, delete our connecting line, and click this blue line here. We can finish our connection. And also, let's say our systematic specific impulse. Let's say constant again. Enter systematic. It's merely one m in this word systematic. I always incorrectly pronounced it to be 2m in these words, which is my bad habits. So our systematic impulse, specific impulse, specific impulse, which is ISP is equal to, sorry, its unit is second. So the value of this ISP is equal to, let's see, is 500 seconds. All right. And now we select this output module and Control CV. We can create another output module, and let's say this output is ISP. Let's drag it to the right place, and again let's type constant, enter it, and say it's total velocity increments. Alright, we can just here. Total velocity increments. Oops, I always change this. This is typing method. Sorry, capital with the first. Total velocity increment, which is the delta, the capital delta V, which is an unit, the unit of this is meter per second. So let's say it's 20. All right, it's 20. Drag to the right place, and also let's control and paste it. You can just follow my step, and you can create your own Simulink programs. So let's say it's delta V. And let's go back to our English version. You can say there are 3 output here. If we want to make it more intuitive, we can place our output. Oops, just remain the same. All right, I give up. All right, yeah. So again, it's a good habit to copy our display module, copy 3 of them, and connect this output. So this one is the delta is the total velocity increment, which is delta V. Sorry, I'll just play this unit here. Is meters per second. So this one is our, maybe it's just delta V. And this one is ISP, which is an unit is which unit is second, and our total mass is m, just m, and our unit is kilogram. Let's run our program. Great. This 500 times 10 to the negative 3 power is equal to 0.5, which is pretty 5, right? Pretty 5. And also, let's display our total temperature. Our total temperature, which is P0 for Pascal units. Maybe it's just epsilon. Maybe it's just epsilon. Alright, I just place it like this. So here we have our geometric design, the ARE. There'll be more design here, but it doesn't matter right now. You can just select all of this module and drag this shaded area and drag it to a fitable place if you like. Now let's create a subsystem for this. Oops, I misselect. We create a subsystem, and this subsystem I may call it oops let's just delete our connection and let's delete it and connect our display module. And let's say this one is our operating conditions. Great. And let's say our operating condition, we can customize our types, our style. Let's say our style is this operating condition is green, and the background we may say I prefer to use a color like this, which is suitable for my eye. If you just look for too long time when you face your screen, it's better for your eyes to set this the background of the Simulink to be the yellow color. And our geometric design, we can also enter more of the geometric design here, but now it's just fine. Oops, maybe we can just sorry. Let's just say it's expansion ratio rather than the geometry design. All right, expansion ratio because the geometry design is not so intuitive in this epsilon expansion expression. Expansion ratio is multiple. All right. Just for a second. All right. So let's see what's next. This provided engineer, but we may want to enter an operating temperature T0, which is less than 333.15 Kelvin. Let's double click in our operating conditions, and let's say, oops, let's say a constant here, and let's say the constant is our indicate T naught, indicated total temperature, total pressure, total temperature. Of the chamber. T0, which is K. So let's say it's 0. Sorry, it's not 0. It's 333.15. Let's drag it. Great. Also, we can also create an input for backup. And this one is our total temperature. Zero prime. Input called total temperature 0 prime. And our output, there's also an output. So it's an output. Output to, sorry, it's not title, it's total temperature. T0. Maybe just T0. We can type a gain here and set its value to be 1. And let's say it's just total temperature, it's just input temperature. Oops. It's just copy, and let's say the gain is, and also let's control and oops. Let's select and control paste it. Let's say this output total temperature, and connect our output. So let's connect this too, because we need to solve the total temperature T0 with a function, with an equation that is not linear. So we can it's unable to just directly solve this equation. Maybe it needs to add some specific Simulink module to solve the equation. I'll do this later, but this one is necessary for now. All right. So let's say let's make it a sum module, and double click this sum module, and let's say this list of signs is plus minus, and type enter it, and connect the input and the output to the input of this module, and say if I drag this input triangle to this line, oops, how does it not work then? All right, let's just drag here, and let's say it's if let's make a judgment here. Let's say make a constant 0. Oops, there's no constant here. We just need to a switch. If this one is greater than 0, the input will, let's say it's just constant, a 1 or 0, constant for 1, and constant for 0. Let's say our output is meet or not. And let's, oops, this total temperature is not necessary here. So let's select our display module and control and paste it. Let's say it's T0 with units Kelvin. and Control and paste it, and let's make some notes here. If satisfied, sorry, satisfied, just satisfied, E is 1, otherwise 0, which means the design failed. So let's connect our meat or nut. Great. The indicators for design, we may want to change its background to be a blue one, and our thermal properties of the gas, we may change it to an also blue one, so that we can just change this to this of the two. So what's next then? The next is the pressure expansion ratio, right? And the temperature expansion, the pressure and the temperature expansion ratio. So let's create some constant here to represent these two expansion ratio. Let's say it's input. It's input. Let's say its expansion ratio is C zeta E prime, and let's say an output is zeta E. Oops, I type it to zeta 3 instead of rather than 3. And let's type gain. Its input is a input pressure expansion ratio. For longer. So its output is output pressure expansion ratio. Great. And let's say the display of this ratio is pressure expansion ratio for zeta E. All right. So we're left with an input of the zeta E. So next, let's create we can just copy and paste it. And let's say it's not zeta E at all. It's CE for the temperature expansion ratio. Of course, this one is CE for the output of the expansion ratio. Is output temperature expansion ratio rather than our pressure. Pretty 5. Just great. Pretty 5. . So let's copy our PRE to TRE. Now it's CE anyway, rather than data E anymore. And connect our CE. Now for backup, let's type in some constants. Oops, I split it. Double click constant again. Let's say if it's worked for now let's run our program to see if the result is correct. Alright, the Pascal. The total temperature is 2E plus 0.5, which is the 2 times 10 to the 5 power. It's correct at T0. Oops, T0, we didn't have a, let's say it's backup constant. I'll delete this backup constant when I finish all the program. So let's calculate again. Alright, it's true. It's satisfied. So next, what's next then? A correction factor to be introduced later. Alright, let's create a current constant here. Or maybe it'll be better to put into our geometric, let's say our subsystem, and let's say the subsystem is for our geometric design. For trick design, I'm going to put my alpha, beta, and lambda here. So let's say this one, let's delete it. Constant, let's say this alpha. Constant, and this one is for beta. So this output, let's copy and paste it. And lambda, finally. Oops, I double click on constant first and renamed it as the lambda. The default unit of this angle is radian rather than degrees. So I need to transfer the units from the degrees to radians if we want to input this. So let's say this one is lambda, and again let's copy and paste it. Say this one is alpha. Oops, this alpha. Let's say this alpha is alpha output, alpha out. Oops, alpha out is U rather than Y, and this one is beta out. Let's say this beta in. This one is lambda out. No, I mean name it just as the degree. And it's not out, it's just alpha. Alpha for radian. And this one is radian. sorry, I don't need any constant here, it's just lambda. So let's type some gain here and name it as the is the converging sections half angle and angle in degree. Control and paste it. It's diverging section half angle in degree. We need output with the in radian. So control and paste it. It's ds. Pretty 5. So now let's convert a gain means degree to radian to rad, and let's say let's type a mux which combines this. Let's enter dmux and connect this to, and this one is, let's delete this middle line, and this one is alpha degree, so it's for alpha degrees, and this one is conversion degree, so it's for different degrees. Degree rad to rad is it needs to times pi over 100 to transfer it to our radian, our radians. Pretty 5. Let's expand it. So what is our lambda then? Oh, let's say I just a little bit. I didn't sleep well last night. Let's say it again. So no, not again. We need a constant. Constant will be 1, and beta. Let's say a cosine. A cosine for our degree, for our radian. And the cosine will +1. Cosine of beta +1. So we need to add a plus or sum. And divided by 2. So let's type divide, right? Let's type constant again and name it 2. And here is our lambda output. And let's say our alpha in degree is 45. Our beta in degree is 11. So let's exit and expand it a little bit. Make some here. is half angle. The alpha is the converging section half angle. Half angle in degrees. Thick. So let's just copy and paste this word. So it's ds rather than cs. Beta. For this reading and output, so we also need to add an whatever, let's say it's lambda. Is our correction factor. Correction factor for, oh, it's just factor lambda. Or it may be better to type correction factor for thrust. It's a thrust correction factor. My English is a little bit poor in this case. All right, so we need to add an, let's delete this connection and add a mux. And add an dmux. And let's say the gain is rad to gradient, radian to grad, rad to degree, rad to degree. So let's run our program to see if the correction is, oops, I didn't change this. This gain is 1 times over pi is 180 over pi. So let's run again. 35. This is our thrust lambda. And let's say our geometric design, the background color to be maybe magenta. And our epsilon ratio, we can just remain white here. It'll be better to separate this one for a little bit far away, just a little bit far away. Good. Pretty fine. All right, so let's put back on our first design. So we've prepared 3 ratio here, the 3 ratios here. The area expansion ratio, the PIE, the pressure expansion ratio, and the temperature expansion ratio, zeta E and Xe for each. So the next part is our correction of lambda, which is introduced here. And there are some other assumptions it will be noted later. So let's say our demanded thrust, desired thrust correction factor, total Xe epsilon Ce, that will be solved later. And finally, it's our geometry indicators. This one will be the output of our programs, so we can just ignore this right now. Oh, maybe we can. It's a great habit to set these subsystems here. So let's just make a backup parameters to be solved. Let's say subsystem, and let's say those are parameters to be solved. Oh, leave it away. We'll do this. We'll solve them one by one by our calculations. There's no need to prepare those bunch of things right now. It'll just increase our pressure. So the first one is the ratio, the P naught and the PE and the ratio. So the P0, let's say our P0 is our P0 is in our, maybe it's in our operations. Its P0 is set above, and what we need is the zeta, the pressure expansion ratio. And let's say our expansion ratio needs to be solved by epsilon and gamma, which is a nonlinear equation. So let's just prepare some subsystems to solve this equation. So we need to close it. We create a subsystem and then we need to solve for zeta E. Zeta E, greedy phi. Let's say this one. So our input will be the epsilon and gamma. But for our circulation, we may name our output to be the epsilon rather than the zeta E. So this input can be the epsilon. It can be the zeta E. And let's say our input to be the gamma, the lowercase gamma. So let's just connect and do our calculation by modular programming. So the first one is constant. Let's say it's 2 for our gamma. So first of all, we need to constant for 1 and add a plus gamma plus 1 and 2 over gamma plus 1. So we need to add a divide module, which is 2 is the factor. This one is the denominator. 2 over gamma plus 1. All right. So now we need to create a power module. This power module, we need to uncheck this signed power to make it a absolute one. This means u to the power of v, and u is the input on the top, and v is the input on the bottom, on the input 2. So this 2 over gamma plus 1 is the u. So we need to connect this to the input. And next we need to get our v. All right. So let's make another constant here to make it more intuitive. And it's minus this time. So it's 1 over minus 1. So let's say it's gamma minus 1. Also, let's create another constant with the value 1. And we need to create a divide module is 1 over gamma minus 1. So we may change the order. 1 over gamma minus 1 to be the power of the v, to the power v. All right, so here is a gamma minus 1. One over gamma minus 1. And this one is 2 divided by gamma plus 1. Pretty fine. So here comes our square roots of the plus 1 and minus 1. So it's gamma plus 1, and this one is gamma minus 1. So we need to create a connection between these two modules, this output, by our divide module. To connect these two, we may need to drag this bunch of things a little bit far away from. Good. So it's gamma minus 1 be our, let's change our module again. It's gamma minus 1. Gamma minus 1 to be our factor to our numerator. And our denominator is gamma plus 1, right? So it's our, oh, I just leave it as divide. And let's take the square root of this. Let's type square root, which means the square root of u. So this one is the square root of g minus 1 over, oops, it's g plus 1 rather than minus 1, rather than g minus 1. Right? Oops, it's minus over plus. My head isn't getting clear today. So they are all factors here. So we need to times, we create a product oops, product of the two. Let's make sure it's right. Great. So here is our n. It's n for numerator. Oh, I have to admit that I didn't sleep well last night. This one is our numerator, and next we'll create our denominators, which is closely bonded with our zeta e, so it places our zeta e down there. Pretty fine. So let's take the power. Mm. Oh. I'll check the sine power. So it's our zeta e, and we need to copy and paste it because there are two power of zeta e. Power 1 and power 2. Power 1, we need to take our gamma, and let's say is constant 2. Right? So let's take a division, which is the power of this one is 2 over gamma. So 2 is the numerator and gamma is the denominator. Oops. To make it more intuitive, I may change this order. So let's delete it. 2 is the numerator and gamma is the denominator. And this one will be our so next one is our gamma plus 1. We can just take the gamma plus 1 here. We also need to create a divide module, and gamma plus 1 is our numerator. We can just connect it, and the gamma is our denominator. We need to connect like this one. So let's combine it and take our 2 a little bit longer. is 2 over gamma. Two over gamma, and this one will be gamma plus 1. Let's make a parenthesis. Gamma plus 1 over gamma, right? Great, is gamma plus 1 over gamma. So which will be the power, make it a little bit longer here, the power of the U of the zeta E. So we have the 2 power, and let's just minus it. Let's make a minus. It's the 2 of the gamma minus, minus our gamma plus 1 over gamma, and take the square root. So here is our square root, which is for denominator. This one is for numerator. And what we need is the epsilon, right? So let's take the epsilon, and we need to divide those two. So let's take a divide, and is our numerator over our denominator, and output our epsilon. Remember, our zeta E is unknown. Oops, there's an untitled here. It's solve for zeta E, so we need to input our gamma and our zeta E. Oops, I just clicked some time plot here. There's no time plot. There's no need to be the to get a time plot. What we need is just merely our input of gamma. So our gamma is known to be 1.4, right? So let's say where is our gamma? It has to be here, right? So let's take our gamma to input this gamma. And what about zeta E then? What about zeta E? How to solve the zeta E, right? How to solve the zeta E? Here comes the question. So what do we know? We know our desired ratio. Where is our ratio? Our epsilon here, right? But what we don't know is zeta E. So we need to take a sum. Oops, I mistaken. We take a sum, and let's say it's minus rather than double plus. Let's say it's minus, and one of them is our design epsilon, and the first one is the second one is our calculating epsilon. So let's change our words here, add some annotation, and let's say it's the difference diff of epsilon. we may want it to be a 0, so we need to add an algebraic constraint module. This one means that we need to solve the equation fz is equal to 0 because the function, the epsilon is a function of the zeta e, the gamma is already known. So if we can solve for this difference between our desired epsilon to our calculated epsilon to let it be 0, so that we can solve our z. To solve this equation, this nonlinear equation, we need to open our solver and change our type to be fixed fixed steps, and oops, it's variable steps. Sorry about it. It's variable steps, and change it to ODE 23T, which can solve this equation. So let's say this one is solve for solve the equation, and this z is the zeta e here, represent the zeta e here corresponding to the zeta e here. So let's connect from the tail to the end, the input and output, and let's say what will we have here. What will we have here? Gamma is 1.4. All right, it's correct. Oh, I forget to get an display here, so that it will be much more intuitive. So this one is our molecular mass, and for kg per mole, to better our calculations, we may need to change our display. So let's say gain, and this one is from g per mole to kg kilogram per mole, and the value of this will be 1e negative 3 which means the 10 to the negative 3 power. So this one will be our m. So let's say our initial value is equal to 0.01. All right, so let's solve it to see what is our result will be, and then make a display here. Oops, we need to type a display here. All right, so let's say it's our zeta e solved, and connect the end of this one. So let's run our version. Pretty 5 is 0.007306. So this is our zeta e solved. So we will attempt this zeta e in our later calculations. So this solve the equation, this algebraic constraint is quite useful in this Simulink in our design of in our calculation of this thrust. So next one, what's next then? We get the zeta e now, right? So let's move on to to our PE. So the ideal exit pressure, we need to create a constant, an input or the output of this one to obtain our P naught to PE, sorry, PE by P naught. To obtain our PE by P naught, I have a poor vocabulary and I'm programmer. So it's a zeta solved, it means the output. So let's take the P naught here, and let's make a type subsystem will be better. Let's say it's solve for PE. All right, let's expand it. And let's say its input, one of the input is the P nut, and the other output is the zeta E, and the output will be our PE, which indicates the exit pressure. So let's say our product model connected to and output PE and get a display here. Get a display, which means the exit pressure. Ideal exit pressure. PE Pascal. So, oops, I just need to create a little bit. All right. So let's connect our P nut and our zeta E just solved right now. And we'll get our ideal exit pressure. So let's run. All right, we're getting 1,461 Pascal to be our ideal exit pressure of the nozzle. So let's continue to move on. The next one is the definition of the gamma. So we need to create a subsystem because the function can be quite complicated. And let's say this solve for its coefficient. Gamma. And the only input is the lowercase gamma. So let's say it's gamma. And the output will be the capital gamma in Greeks. Pretty fine. And let's say, where is our gamma? Our gamma is here. Oops. About this part, I need to mention that we can also create an output of the ideal gas of the gas constant for nitrogen, which is no bar on the top. The relation between this gas constant to the universal gas constant is just simply by a divide. So the numerator is our R bar, and the denominator is our output N. Let's move a little bit. All right, so here, this one will be our gas constant. So let's say, oops, I just mistype my keyboard. Don't worry about that. So it's our R bar, universal gas constant, which is R bar for joule per mole Kelvin. And this one is our nitrogen gas constant, which is R for joule per G kg dot kilogram dot Kelvin, because it's just we can just exchange that for this one from gram per mole to a kilogram per mole, and when it's divided by when it's divised about the R bar, the mole will be replaced. The mole will be replaced by the kg. All right, so Let's connect our constant. Oops, I misclicked. My brain didn't get really clear today, to be honest. I have to admit this. So back on our gamma. Let's say our gamma and our capital gamma has the relations of this complicated equation. So let's take the square root of the little gamma here. And this will be our factor 1, and our factor 2 will be our a constant. Let's say it's 2, and create a constant 1, 35. So let's make a plus. Is gamma plus 1, and divided by 2, or divides 2. It's divides 2, not divided by 2. So let's change this order. So 2 over gamma minus 1, and take the let's make another a minus. So we have the power is the minus gamma minus 1 minus 1, and let's say the product. So 2 times gamma minus 1 to be the denominator of this power. So let's say it's 2 gamma plus 1 minus 1, and it divides the gamma plus 1. So let's say a division here. Oops. Division here is the denominator, and the numerator is the gamma minus 1, minus plus 1, gamma plus 1. All right. So we have the power. We have the power, and let's take is 2 over gamma plus 1. So it's our power, it's our u here, and this one is our, oops, I just misdelete. This one is gamma plus 1, right? Over 2 times gamma minus 1. So let's expand it a little bit. Oh, I need to add a middle parenthesis to clarify this in order not to mistaken. So let's say a power. So the power will be the on side. So it's 2 over to be the u, and this power 35. All right. So the final part, let's product. Oops. Let's take the product. Take the product of the two. First one is our square root of gamma, and the second one is this bunch of naughty things. And we take the great gamma here. 35. 35. That's great. A bit more. All right, I'll be. I'll just move it. Pretty 5. All right, so let's take the gamma here to connect this little gamma to this gamma. Say, all right, pretty fine to connect this. And let's display our gamma. Let's display. So let's run our program to see the results here. Pretty fine, pretty fine, pretty fine. All right, so let's move on. So let's solve our demanded thrust. Here comes our thrust. So let's say I solved our subsystem. So the first one will be our M. Let's copy and paste for 4 input because we will need to solve the mounted and the design thrust at the same time. And the second one is the ISP. Sorry about it. It's the delta V rather than ISP. Delta V. And the third one is the ISP. And the fourth one will be our lambda. And finally, the first output will be our thrust F prime. And copy and paste it to be our F. So by our momentum theorem, we need to take the product of M and delta V, which means the total impulse, and divide it by ISP. So let's take the divide is the numerator and ISP is the denominator, and we'll get our demanded. Thrust. Demanded thrust. And if we times this time is divide, our demanded thrust by lambda, we get our design thrust. Loads of this so at the same time we take the display module. So this one is our module for design. Oh, oops, demanded F prime for maybe millinewton will be a better. So this is our design. But by the ISO units, the output of this f prime and f are all united by n, by Newton. So we need to add a mux to combine these two variables and make a dmux. And we'll add, and we will add a gain to transfer Newton to millinewton. The value of the gain is 1000. So let's expand this to make it more intuitive. Pretty fine. So let's run our program to see the results. Oops, I mistaken it because I didn't take the input. So I need to connect those inputs. The first one is our M, our mass, and the second one is our delta V, and the third one is our ISP, our specific impulse, and the delta and the lambda will take the result we just calculate in our geometric design. So let's calculate it again. Oops. So our demanded F prime is equal to 20 millinewton, and our design thrust is equal to 20.19 millinewtons. We can see that the design F is a little bit greater than the demanded thrust. So let's move on. So we have solved our design thrust and our demanded thrust. So the next one will be solved our CF redefined. So by our complete expansion assumption, PA is equal to PE, right? So for the sake of keeping the completion of this formula, I'll do this one by one, not for the simplification, just for our original. So we may need to create a subsystem to contain our ambient condition. So let's double click and let's say our first input is the PA. All right, PA prime, and the output is our PA. Oops, I mispasted. Let's copy and paste our input. And let's say this is TA is the atmosphere. Is the temperature of the atmosphere, the ambient temperature, TA prime. Let's control and paste it. So say it's a TA. So we no need to change these things for any. We just keep these things here. So let's say our PE has already been solved, right? Here is our PE. So let's make a gain here. Because this ambient condition is quite important, so I need to strategize by brown, maybe brown. So here is the complete expansion assumption. Oops, it's assumption rather than assumption. Let's connect the PA with our PE. So let's just select the input and take the output of the PE 35. Of course, we also need to add a display here. Ambient pressure PA, which united in Pascal. So let's connect and let's just copy and paste it. It's ambient temperature, which is TA united in Kelvin. So let's connect the input and the output. This TA will be calculated by our T0 and our by our T0 and the CE, the temperature expansion ratio, which is not solved yet. So we may need to connect it to our backup constant. Let's see, where is our backup constant? Here. So all right then. For our we may need to delete this bunch of things because let's just delete our TA first. We need to arrange something because the zeta E is already solved. Yeah, it's already solved. So let me see. It's our zeta E. We need to delete this part and connect our zeta E to this one. And the CE oops, we may no need to get this bunch of things here. Get this bunch of things here. So this one is unnecessary anymore. This one is unnecessary anymore. Well, whatever. Well, I'll just keep it here. I'll just keep it here until I solve all the equation. Then I'll delete it. Oh. All right. Let's see. Our TA. So let's take our backup constant 1 and connect our TA with the 1 with the constant 1. Let's see if our project can be worked. Great. Because these of the things are the things we need to take into consideration. So I may try to divide by blue, blue, and blue. and this demanding will be red. Red. All right. Half angle will be our magenta. This will be magenta. The thrust correction will be magenta 2. The ambient pressure will be this one, 35. So this backup will not continue soon. Will not continue for so soon. So let's take our CF subsystem. Which is for the coefficient, the thrust coefficient. Coefficient CF. So the output will be CF, which is a dimensionless. So let's say it's the let's say our display. By the way, for this PA, we need to add a constant to back up our PA, because we may want to do the ground trial test. So let's say it's our backup. Backup PA. Oops, it's not capital, it's lowercase. Let's say it's 1.013E5 in Pascal. And the TA may be another constant, which is let me see. Let's see. It may be 300 in K PA Pascal, and this one is K Kelvin. Backup TA Kelvin. Alright, so we'll leave this outside. Just in case that if we want to do the trial, the ground trial test, we can just change these things as the backup. So let's back on our coefficient. So we need 1, 2, 3, 4, 5, 6 input. So let's just copy and paste 6 of them. Oops. The first one will be the gamma, the capital gamma in Greeks. And the second one will be the lowercase gamma. The third one will be our exit pressure, which is PE. And the fourth one will be our total pressure, which is set to be 0.2 metapascal. And the final will be our, and the fifth one is not the final, it's the fifth one will be our PA, which is the atmosphere, ambient pressure. And the final will be our epsilon. So let's do it one by one, then it will be a great calculation. So let's take the 2 gamma over 1, gamma minus 1. So let's take a constant. Let's say it's, constant and another constant valued 2. All right. So let's separate this input a little bit to turn out our space, save our space. All right. So the first thing is to times make a time. So let's double click and make a product. Two and make a minus. We change the order. So it's the gamma. And let's take the constant. So let's indicate that this one is 2 gamma. And this one is gamma minus 1. So let's just divide these two things. Divide is 2. We need to change the order to make it more convenient. It's 2 gamma over gamma minus 1, right? Alright, so here we get our 2 gamma over gamma minus 1. Pretty good. So the next thing is the 1 plus this bunch of things. So we need to take the division of PE by P nut. PE and P nut. So let's take the division. Divide is PE as the denominator and the P nut by the PE the numerator. So is PE P0 and take we need to take the division of the gamma minus 1 and over gamma. Alright, it's gamma minus 1 over gamma. Make sure it's right. Is gamma minus 1 over gamma. This will be the u to the v power, the u to the power of v. The v will be this gamma minus 1 over gamma. So let's take our power. So this one will be our u. And our gamma minus 1 over gamma will be our v. And let's take the minus. So this is the minus part, and 1 will be our. So it's so finally, let's take the product of this bunch of things, this 2 gamma over gamma minus 1, and our this complicated minus relations and times, so that, and take the square root of it. Take the square root. Let's take the square root of this bunch of things and times our capital gamma. Oops. The product. So let's make a minus here. Let's make a divide. Let me change the order. Let's say it's the PA over P0. PA over P0. So it's PA over P0. And get a minus relationship. So let's make a minus. It's PE over P0 minus PA over P0 and times our epsilon. Let's make the product. So finally, let's make a a plus rather than a minus. Plus of the two. Oops. And when we're finished our plus, then we get our CF, which is quite a naughty thing here. So let's expand it and take our gamma. So the first thing is the gamma will be, oh, where is our, will be our gamma then? I need to get it a dangerous red here because this one is quite important. So let's take our gamma first. Let's expand it for a little bit. So where is our gamma then? Aha, it's here. So let's create a gamma and a little gamma with here. And our PE with our dissolved P exit pressure. Exit pressure, where's our exit pressure then? Let's see, it's here. All right, it's connected well. It's connected well. Pretty good, pretty good. PE is equal to PA. Pretty good. And now let's say our P0. Our P0 will be found on found here, maybe here or there. It's here. It's our P0. So let's take the P0. Take the P0 here. So and next is our PA and our epsilon. Epsilon, where's our epsilon then? Our epsilon is for the sake of, I need to display the difference between to check its convergent, checking convergency. So say great. So the final part is our CF, which is the coefficient CF. greater than 0. All right, so let's run our model to check our results. It's greater than 0, which is fine, which is pretty fine. All right, the difference between our final results, the desired area expansion ratio, and our calculated AER epsilon deleted, and it's connected to this epsilon here. So let's run it. It's totally the same, which is great. All right, so what's next then? Here is our AT. Now it's our AT, right? So we need to create some subsystem and name it to be the geometric parameters. So let's expand. It will be a long subsystem. So the first one is our throat. Let's delete. Maybe there will be three for yet. So 1, 2, 3. One is the design thrust, which is F, and our P0, the total temperature of the chamber, and the throat, AT. Oops, it's not throat. It's our CF. So it's our CF. Mid-range here. All right. So let's calculate our AT first. Our AT will be a division. And we need to create a product first, which is the CF times our P0 and divides the design thrust to get our AT. So we may not output our AT first, so we just AT first, the throat of the cross section, the cross section area of the throat. Oops, I need to delete it. So here comes our AT, which is a core of our design. So the next one is our epsilon. Input says epsilon. So if we times our epsilon by our AT, let's say it's product, take the product of the two. Oops. Let's take the product of the two, and we'll get our AE. So nextly, let's take the diameters. We need to get a constant. We may not get a constant. All right, we also need a constant. Just get a constant here, and let's say it's pi. And let's say it's AT divided by time by pi. So it's divide. Let's change the order to make it more intuitively. So it's AT divided by pi and take the square roots. I make a lot of jibber jabber in this video, so if uh, if you need to correct me, just do correct me in my comments below. And let's take the 2 times of it. Let's gain. And here comes our diameters, which is the output. Is the dt. So for the sake of convenience, we may want to make a box. Let's combine this area things. And get our times. And will be an output. So we can take a demux module. And let's delete it. Let's copy and paste it. So here is our DE. Pretty fine. All right, let's adjust the position to make it more intuitive. So what about the DC then? It's empirical value, right? So we can just times. We got constant here. Oh, you can just gain. We gain the let's say it's 1 over 0.19. Expand it to make it more clear. So it's empirical. And output our DC, which is the diameter of the chamber. And next one is our LT. So we need more input. The first one is our alpha. And the second one is our beta. Notice that the alpha and beta are already are input with the degree in degree, so we need to mux them together to transfer into degree to rad, and the value will be pi over 118 and 80. So let's demux them. Demux them and take the we take the tangent of it same time. All right, let's just expand it. Pretty good. And the tangent times 2 will be the dt. So we can just divide it separately. So let's make a gain. And let's say it's the 2. let's say it's the denominator. Denominator, pretty good. And our DC is solved here. So let's take the minus. Oops. Let's take the minus. All right. So the first one is our LT, which is DC, minus DT. All right, it's DT. It's for the alpha. So let's take a divide here. Divide the module. And this is our numerator. This is our denominator. And let's make another minus. So this one will be the DE minus DT. So let's find our DE then. It's here. So let's just connect these two and our DT. Pretty good. And let's make another divide. This one is our numerator and this one is our denominator. For alpha. And this one is for beta. To make sure it's right. So next, let's conduct our output. Our output. So let's say output. Enter it, and let's say this one is LT. And control and paste it. This one is LE expansion. So what is the final one? It's the LC, right? So what is the LC then? What's the LC do? The LC is equal to 5 times the diameters of the throat. So let's say it's a gain. Let's say 5, and it's also empirical. For this one is empirical for LC this time. So LC is equal to 5 times the diameter of the throat. So let's find our diameter of the throat here. So we can just connect this one and get our LC. The output, as the output is LC. Let me see. It's LC. Great. Now, let's move on. Here comes our final curvature radii. They are all empirical, so I'm going to just just uh just do it one by one. So let's say it's there'll be three gain here, dt, de, dt, dt, and de. So maybe two will be all right then. All right, just do it one by one then. Just for not, just for not to, just for not mistaking any coefficient. So the first one is 0.25, and this one is empirical for R1, which is times the dt to get our R1. Oh, we'll delete these two. Let's copy and paste it, and let's say it's empirical for R2. And the value will be 0.5 for our throat. Empirical for R3 is also 0.5, but now it's our DE. Sorry, I miss input the capital E with the in the subscript of the D of the diameter. I'll correct it later, but not now. So let's just copy and paste it. All right, let's connect them. So finally, we get our all of this bunch of things get them done. So let's just quit and turn it to a green one. Maybe a little bit deeper. I also need to stretch it for a little bit longer. So let's do our display work. Oops. Display here. All right. So here is the diameter of the throat. dt. Let's say it's for all of these bunch of things are quite small in size, so I need to get a mux to expand them. Let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 of them, right? So let's say it's 9. Oops, I misconnect again. Oops, what happened to me today? What's on the world? So let's gain it by gain is 1,000 just for meters to millimeters, and with demux them. With demux will be also be 9 here. Now let's copy and paste. And the second one will be of the exit which is DE, and the third one, well, maybe we can just expand it a little bit longer. So there is the of the chamber, is the diameter of the chamber. And the third one is the diameter, is the length of the throat. Length of the throat. Oops. Which is LT. Great. And oh, sorry, it's length of the expansion, the convergent part. So it's not sort of doesn't own a concept like length. This convergent section is length of the diverging section. Diverging section LE. Pretty good. It's divergent, right? Divergent, and finally is length of the chamber, which is LC. Pretty good. And final is our radii. Radius of the chamber to cross converging section are 1. So maybe it's not so normalized, or maybe it's not so I don't know how to say. It's not so standard. Maybe the naming method is also standard, but just for our convenience. So it doesn't matter at all then. So converging section throw to diverging section, which is R of 2, also united in millimeter. So the final is our diverging section to exit, which are 3. Pretty good. So now let's connect our input and output. So the first one is our design thrust, which is here. All right. And our P nut will connect to here, and our CF, the coefficient, will be conducted to here, and our epsilon will be conducted to here. Pretty good. And finally, the alpha we conducted to and our beta will be conducted to so let's see if we can solve this, run this program. Pretty good. So what now then? Our alpha, beta, and those are all transferred into this bunch of things, and what we get is these things here. So what's the point of these things then? What's the point of these things then? It's our AT. It's our ATCF and P0. Our P0. So our P0 is equal to this one is phi, and our CF, and here is our CF. See, and our epsilon is defined to be 10, and our alpha and beta is by degrees, and this one is also degrees here. So here is our our results. Maybe it's not so standard or correct or any else, but whatever. We can just leave it here. We can just leave it right now. Maybe some of the things will be corrected later. For this. Oh. My head is getting clear right now because I've already been doing this video for a little bit long time, right? Now whatever. The final part is going to solve for our T nut to prepare for our this data, this result data is a little bit strange here. A little bit strange here. It's a little bit too long. All right. I'll check this one later, but for now. square root the AE. Oh. Oops, this bloody F. I cannot enter it into the unit with the units 10 because I need to. I need to connect it to this part, rather than. Or I can just. Or I can just. Oh, sorry, forget about it. Let's calculate mode. This one is much more common. This one is much more common right now. Pretty good, pretty good. So let's continue our programming. So our gas constant is already calculated out, and next we're going to figure out our mass flow m dot. So let's create a subsystem, and let's say solve for m dot. So the output will be the rm dot, and the input, maybe there are 5 inputs here. So let's copy paste 5 input. The first one is the capital gamma, and the second one is our P0. The third one is our AT, which is already solved, right? And the fourth one is our R, our gas constant for nitrogen. And the last one is the things to be solved, which is the T0. So let's just delete it and arrange those things. So let's take the product and turns into 3. So the first one is the gamma, the P naught, and our AT, which is already solved out, and our square root of we may take a more product to combine this R and T0, and let's take the square root of this denominator. Better. No additional need. Let's do a more divide operation of these two stuff, and we'll get our m dot. All right, let's expand it, and also get a display of the m dot mass flow. Dot, which is kg per second for ISO. When we need to meet a gain here, and let's say it's kg to g, and the value of the gain is 1000, and let's say it's G per second, which will be much more intuitive. So let's connect those to stuff. Connect this stuff. And our P0 is already solved out to be here. So let's connect. And our AT is oops. We may need to change our AT into DT because we output the DT and get a calculation to turns into AT. So we may get a gain here. Oh, oops, we need to get a gain. Right, it's gain 5, which is the RT. And let's get a square of it. Square, make a power. Power. Oops, I mistakenly and a constant of 2. All right, and let's gain our pi. Inputting this one, so that great. And our gas constant for nitrogen is solved in. And where is our nitrogen? Where is our gas nitrogen then? Let's see if it's here. Ah, it's here. We should be pay attention to the units here very, very carefully. And our T0 is the things to be solved. We may want to connect it to our T0 here. So let's connect it. Remember, the T0 is to be solved. Is to be solved here. So let's see. There is ambient here. We'll be cross this backup constant very, very soon. So let's make sure this unit is correct. All right. So next is our ideal exit velocity. Make a more subsystem, and let's say is ideal exit velocity VE. All right, just VE, and our input we need the lowercase gamma. So let's just copy and paste four input here, and the second one is the gas constant R. The third one is the T0, again the T0. And the fourth one is the zeta E, which is also solved already. So let's just click it, and let's say it is our VE. So what is this bloody equation? Let's say we make a constant here to name it 2 and constant 1 to facilitate our calculation. So let's just take the product of the 2 and the gamma. Oops, I misconnected it. And let's say it's a minus. It's gamma minus 1. So this one is 2 gamma. And this operation turns out to be the gamma minus 1. So gamma minus 1 and 2 gamma, we take the division of it. 2 gamma is the numerator and the gamma minus 1 is the denominator. And next, let's times our product. Let's make it 4. The first one is and the fourth one is a little bit complicated things, which refers to as zeta e. So let's say is gamma minus 1. Let's take it taken division of gamma minus 1 by our gamma. Alright, so next thing is the power. Take the power. Zeta e and get a constant 1 to minus this bunch of things. Minus is 1 minus this thing and turns out to be the fourth product factor. And here comes our VE, which is pretty good. Let's expand it for a little bit. And let's say display. So it's our ideal exit ideal VE for meters per second. I'll make it a blue background because it's a little bit important. So let's connect up gamma. And our R is here. And expand for a little bit. Our T0 again. And our zeta E is already solved here. Pretty good, pretty good. So our ideal VE is shown here, and our mass flow is also an ideal, in fact. Mass flow, which is also important. I'll make it a blue background. So let's just solve for the T nut. Let's combine it with our design thrust. We may want to take our design thrust here um, a little bit longer. Pretty good. And next, we're going to design our subsystem. And let's say our subsystem input have 1, 2, 3, 4, 5 input. Good. They are just simply product and divide and minus. So let's say it's m dot. We should be careful that maybe the unit will be mistaken, so we have to take carefully. And next one is VE, and this one is our AE. Oops, we may take it as the DE rather than the AE, because we need to transfer it into the AE, and our PE and our PA. So back to our vision here. We just take this bunch of things, just copy it and paste it in. So this one is RT, is RE rather than RT. Pretty good. So here comes our AE. Just delete it. All right. So let's take the minus. And times products. Good. Now let's just minus these two things. Let's take the product of the two main variable, the m dot and the VE subscript E. So let's take the plus. And output is the F, is an F. So let's solve for T nut. Let's make a display module, and let's say it's ideal is calculated ideal thrust, which is our design thrust. Which means we need to get a gain here. Let's just stretch it to make it clear. And let's say it's n to millinewton. Oops. Oh. The millinewton will be let's make it a blue, a red background. All right, let's delete it. So this one is important. So let's make it stretch. All right, forget it. I just create another game for. It's n to mn backup. So let's connect this and connect our m dot, which is here. Remember, this one is we have to follow our ISO unit standard, and this one is UEE, and our DE has to be followed by great, and our PE is calculated. Where is our PE? Let's see, where's our PE? My PE has to be related to the zeta E here. Here, I get our PE. So this one, I'll take it as a purple. So the final is the PA. Let's see my PA. Great. Now, let's see if we can solve for this bunch of things. But for a moment, for this f is a function of the t0, so the value of the t0 will affect the value of the of the f, and our t0 prime is divided by this this bunch of things. So we don't need a backup anymore, and we're going to solve this equation by algebraic constraint module. So let's make a sum, and this sum is minus. Let's take our oops, it's not the mountain, it's the design. It's the design one. This is what we want. The diff f. Remember, this one is mm, is millimeter. So millimeter. All right. So we'll just repeat our sections to make an algebraic constraint. It's T0 equation rather than solve for T0. So this one is for solve for T not. So let's connect it and turn it back on to where our T0 located. We need to add a backup T0 constant. This is 315K. Oops. It's 3.15 rather than 3.5 because it's the limit. Max T0. So let's make a derivative of it. Derivative of our of our changing. So and let's make an motive moving average to smooth our exchanging. Though this though these things is unnecessary for us, but whatever. So let's just compare it with 0. Let's make a switch here and change our is unequal to 0. If it's equal to unequal to 0, let's see its introduction. Pass through input 1 when input 2 when input 2 satisfies the select criterion. Otherwise, pass through input 3 which means if this satisfies this one, so it'll pass through this one, and if it's not, it'll pass through this one. If it is equal to 0, then it'll pass through to our this solving equation. And then we can check our common. So let's run our program to see if it works. Oops, we have a Laval solve for T0, so we can be mistakes on. Let me say it's a 300. Let's solve it again. Oops, there may be a singularity in the solution. So let's check. Back up this one and this one. We just do it step by step. Um, I've become really tired for this few days. It's uh N backup, so it's calculated design thrust is this one. So this one have there's something wrong with it with this bloody things here. So I need to check these things one by one. So this unbeaten, it doesn't matter at all. We can ignore it. It's degree, the formula, the factor, lambda. Which is fine. The demanded divided will get our string. So long our zeta e. Let's make it step by step. So I can be mistaken some things here. So road. Pressure. So maybe this bloody thing has gone wrong. Let's say it's greater than 0. What if it's greater than 0? Oops, there's also show some calculations. It's not for this one. Well then let's delete these things and connect to our backup. It didn't go wrong. So let's see. Well then, our calculated design thrust has turns to be a huge amount of these blood things. So there has to be something wrong with it. So let's see what happened. What had happened there? It's PE minus PA. and m dot minus times the 2. I can be mistaken by some. Oops, our ideal VE is too high, right? So let's see what have we gone wrong here. What have we gone wrong here? Our R is equal to this bunch of things, which is fine. T0, and this one is fine. So our gamma. What about our gamma? Oops, we're making display here. Specific heat ratio. Specific heat ratio gamma. Now let's run it again. So it's all right. So what about the T0 then? And now zeta E to be solved. So there has to be something wrong. There has to be something wrong here. What had to happen then? Oh, I forget to take the square root. Oops. Now it's much better. Now it's much better. Right here. It's much better. It's much better. I need to delete this one and connect it to our let's see, where is my design thrust then? Where is my design thrust? Oh, need our design thrust. Now let's check it. Great. So now let's delete it again. We delete this bunch of things and let's just connect. And let's see if it can. Oops, it's also wrong. So I need to figure out where the hell is wrong. What the hell is wrong here? I need to get into. Okay, so it's also wrong here. So solve for T0. What happened? What happened to this one? Total temperature, top temperature, meet or not? It's oops, it just doesn't meet our temperature. Now let's make a display to monitor. Let's monitor our results. For our T not. So let's delete it again. Our monitor for 0 is right here. And this will be our difference. Let's check our difference then. Difference monitor. Let's do it, which is fine. Now let's check our, if we exchange this to 3.115, let's see the results. Which is less than, it's less than 0. So oops, I need to exchange these two things maybe. Let me see. It's never equal to 0, so I cannot just check this body things like this one. So I need to exchange my when the moving average. And next one will be less than or equal. Let's say our converging set converging standard is 1 in. We may need to add more an ABS check. So if it is, and we'll make a switch here. So now, if it's less than or equal to, then it will pronounce 0. And if it pronounces 0, then it will take the first things here. Because it can never be equal to 0, right? So and our max, let's delete it. Now let's make it 333.15, which is our original standard. Oops. The English version, diff of f How can it be then? Oh, I always mistakes those things like this. Now let's run again. Oops, so for T0 went wrong. Um, average is less than or equal to. Let's see. It's true, then you will take this, get things through. If it's wrong, it's not a mess. I may do more testing to check if it's wrong, right or wrong. So it will not be a mess. A max. Let's make it a standard. Oops. Reference. A reference T0 here. So let's exchange it. Let's do no. Make this thing like this. Just less than or equal to. If it's less than or if it's greater or it's not equal to, you print is equal to 0, which will be let's make a switch. So if it's true, if it is less than or equal, if it is less than or equal to, which means it's fine. So we can just input our temperature. If it is not, then we'll input this one. If it is less than or equal to 0, less than or if it is less than or equal to 0, which means the upper temperature is less than 300 is 1. So let's calculate it. Now let's just click it and get our standard. The monitor is 0, which means it's true. True. If it's true, then it will be 1, and our T0 will be 300, which means it's fine. Let's see our. Let's see if our let me check out any wrong. Our mass flow is if our mass flow is right. Less than or equal to. So maybe I just put it a little too hard. So let's say it's less than or equal to this one. Now, oops, solve for T0 is not 0. All right then. Look at this. Maybe it is better to not. It is better not to. Pretty well, which means this data indicates that our our formula didn't go wrong. We just need to pay more attention to this. Let me also hit to rate of change monitor. Rate of change of diff monitor. Now let's do this. The rate of change is less than or equal to 0. Less than or equal to 0. So it's true, and it will input these things into our result. Let's try this. Oops. So it's going wrong. We may add a more monitor to a 30 or so. It always just reported wrong, which is very naughty things here. So let's connect it again. This loop has gone something wrong. We need to debug this whole system to just to make sure. dm.dve, they are all correct. So it's not the formula. The problem of the form. It's not the problem of the formula. Let's just delete it and let's do it one more again. So why then? If it's less than or equal to 0, if it's less than or equal to 0, which means this is 2. If it's greater than the reference, the max. Or I'll delete this bloody things. I'll just connect my to my. It also went wrong. What can be not a number then? Alright, whatever. I'll delete it. I'll just delete it. Connect it to my reference. So, yeah. Oh, just the monitor. It's always reported wrong. It does not satisfied. Which means the T0 is too high. Alright, I'll change this. If it is less than, initial guess. It's wheel. Oops. Minus over 0 t0 is equal to 0. How can it be? What if I set it to 300? Something went wrong. Threshold. directions. Oh, I see. I shall never attempt this one. I need to attempt this one. Now, maybe I need to be a little bit more sharpened than that. Let's see the difference. Oops. So why my thrust always ends up like this? I need to check a display module to so it's 100. I did obtain this those bunch of things then, and this one times this one. Now let's times and see. What have I done? t is less than or equal to 0, obtained. Get to and we create another subsystem to solve for our demanded exit velocity VER. It creates an F prime, and let's just control and paste. And dot dot and a e and PE and P. So at the same time, we need to solve our VER. So let's just delete it, and by take a minus. Let's say let's put a times product. Take the product of these two, and let our thrust get minus these things, and divide it by our m dot. We get a V version. So this is our display, and let's say it's our demanded exit velocity. Let's connect it. Let's connect and connect the m dot. We just calculate it. And the AE, oops, we may want to be a DE again. And let's talk together this bunch of things too. pretty good. So let's just comparing it, right? Let's make the background blue, and we run the program. Oops, it's not blue. I don't want this one to be blue. I want this one to be blue. And let's comparing it. So let's just run our program. And if I change my initial guess, let it be 300. All of these bloody things will be changed. Alright, so now we finished our simulations, and finally we get this backup deleted, and we obtain a CE to design our to solve our exit temperature of the definition by the definition. So um let's say my temperature is like C is a subsystem. We create a subsystem and naming it CE solution, and my input are gamma, and control and copy it, and the other input is our zeta E, and our output is CE, which is the temperature expansion ratio. So let's make a constant here. Then here I have like a minus. That's that's gamma minus 1. And make a division. And read to the power. Oops. Nice. Power is gamma minus 1. Let's take the power. Sorry. The power of these things above, and take the, and here it comes the CE. So let's expand it to take our gamma. Our gamma will be right here. And take our zeta E. So where is our zeta E then? Right here. Here comes our zeta E. So we display this zeta E as well. Oops. Display. So this is the temperature. Temperature expansion ratio. Zeta. Oops. It's CE rather than zeta E. So connected. And let's just um, next we take the product of the pick the product of the CE. Oops, it made me. And we take the total temperature we have just solved here. We may call it a 323. Apply it and perfect. And we get a display. Oops. Show our exit, ideal exit, set temperature TE, which is unit in K. So let's just stop it, run our program. Finally, let's get rid of our, let's make a gain here. Ideal P and ideal T. Perfect. So finally, let's connect our TA with our TE. So run it. Both of them I may call it the deep blue, maybe not the deep blue, maybe the gray. All right, so here I have finished this design of programmer, but there are several details needs to be adjusted, like the mass flow and the exit velocity. The value of these two variables cannot be too strange. It needs to be controlled into a suitable area. So I choose 323K to be our initial guess, and it's just calculated step by step, and finally we get our ideal exit velocity and our demanded velocity. So next we'll do our simulations to check if our simulation results can meet our indicators, just to improve uh, our qualities. So this Simulink file, I'll pack it up and upload to my net drive. I'll put the net drive links below the comment. You can just click the links that's stuck on top and download this program to try different value of T0. You will find out that whether if it's 300, 150, or some other values, the final calculated design thrust will always be 20.19 millinewton, which is very ideal. But the value of the mass the mass flow and the the, the ideal mass flow and the ideal exit velocity will be so strange that we cannot achieve it in reality. So we have to limit it, our m and our v, to just in case we can get a suitable value of these two variables to to attain in our reality engineering. So this is our Simulink works. Hope you can learn something from it. And remember, when you do your when you um, do your differentiations, you have to conduct this connect this output of these differences to your fz and solve for fz is equal to 0 and output in z. The convergence of the z by time is quite important. So I take the derivative uh, of the z with respect to t to compare it with our converging standard 1 times 10 to the negative 18. If it's less than or equal to this value, it will get convergent. It will convergent. It converges, and we can just output our calculated t with subscript 0. But this t with subscript 0 has to be taken into a is a quite naughty value. Alright, I've done so much jibber jabber splash here, so let's just print our screen. And turns into our SolidWorks. Let's put on our desktops. Maybe there are some working conditions to be solved, to be checked. Let's see where it is. It's the thrust formula F. This thrust formula. So let's see where is our ambient. So this is important. Let's just print it, save it. Finally, our P with subscript 0, which is here. This one is also quite important. So we may also want to save it to do when we do our simulations in CFD. So let's say it's our operating condition. Let's see, it's OC. And let's just save it, Control S, save it, and close this Simulink, and close our MATLAB. And let's say this is our geometry design. Metric design. Just in order to check. Oops. And this one is, it's unnamed, is our ambient. Is our ambient condition. I would say it's AC. Alright, so all the things have been prepared. So let's just open our SolidWorks. Now let's create a new part. Yes, great. So let's take the front page and get a sketch. We'll use a spline tools to create our curve of this Laval nozzle. So let's just take our central lines here and let's take this one. So the first thing is our LE is 1.589. So 1.589. So we need to let's just make a smart dimension. Great, good. So Oops, we need to our basic we may need to setting our MBD as general. Say where is our metric units, spin box increment. So let's open our SolidWorks. So all the things are prepared, and now let's open our SolidWorks. Every time I open it, it takes a little bit long time. I already prepared a bunch of things to draw, so right. Okay, so let's take our design. The diameter of the throat dt is equal to 0.2857. So we can just change it here. 0.2857 over 2, which will be our radius. And the diameter of the exit is equal to 0.9036 over 2. 36 over 2, which is fine. The diameter of this chamber is equal to 1.504. Oops, this is stopped, right? We can just change here. It's here. 1.504 2 is which is correct, and the length of the throat, the community section is 0.6091. It's correct, and our length of the diverging section LE is equal to 1.589 is correct, and our length of the chamber LEC is equal to 1.429 is correct, and our radius of the three, the first one is to R1, R1. All right, it's correct, and the R2, the curvature radius of the R2 is also correct, and our R3 is correct too. So all the things are prepared well. So now let's do our graph of the curvature, the curve of the nozzle. So let's just take our center line and grab it, double click and ESC, and control select these two and add a tangent relations. Repeat it again, add a tangent relations, and maybe these two is enough. And this time, and next we select the central line too. Oops, we need to select a little bit longer. Right, good. So maybe we need a control select this line and this circle at the tangent relations. Select this to add the tangent relations. All right, pretty good. Now we use our trim entities to trim those rest. Pretty good. And now let's draw some line. Draw some perpendicular line to the tangent line. One is enough. Good. And trim the rest of the curve. Pretty good. So now let's use our spline. Select it. Select the first point and the tangent point and the cross point. Oops. I need to be more careful because I haven't eaten my lunch yet. So select it and pretty good. So here we go. Here we done our curve, and let's just exit our sketch and select the front place and sketch again, and control select this straight line, this chamber line, and this nozzle line, and use our convert entities. Very good. So now let's just do one more thing. We connect from tail, from head to the end, convey a bolded close shape, and we use our revolved boss. So pretty good. And here comes our Laval nozzle. So let's just save it. we save it as in our Laval Nozzle. Let's just save it's a sample. All right. So let's see if our sample is in our file. So here's our sample. So let's just transfer into S line T. Close our SolidWorks and open our workbench. And you can also open the workbench by just click the icon on the screen. They are working as the same. Now we drag a fluid flow module into the workbench, and we may say it's Laval sample, and we import our geometry, import our sample, and just double click the mesh to enter our mesh editing. We may delete or not, better delete this unnecessary model files. I'll delete it right now. Alright then. So in our mesh editor, in our CFD pre-post, we select the front face and create a inlet face and select the chamber, make it a chamber and the nozzle, and finally the outlet. Pretty good. So now let's check inlet, chamber, nozzle, and outlet, which is fine. So let's just update our mesh. We have to make sure that our solver preferences is Fluent and our physics preference is a CFD. So the mesh controller can be so much more clear and detailed, but I'm not going to do any mesh control in this video. If you need, I'll make another video to introduce how to control the mesh. It's already fine. It's already fine to create a mesh like this. So let's close our mesh editor. We need to wait for a moment. Now let's edit in our Fluent launcher and select double precision and start our Fluent simulation. All right, here comes our nozzle. Let's just check the mesh, and we type reorder and select this order to control and paste it. Let's just enter it to make sure that our bandwidth reduction is equal to 1, just like this. This will increase the speed of converging when we do our calculations, and we select the density-based solve because it's compressible. And let's turn on our energy equation and set our viscosity to realizable K epsilon. And next, let's customize our materials. Let's say it's Laval air, and select the ideal gas and make it a molecular weight. Maybe it's equal to just 28. Just 28. Let's create it, and our operating conditions, we need to choose it to 0 so that we can arrange our boundary conditions. So about inlet, let's just select the type of mass flow inlet and check our, oops, I just misselected. Check our operating conditions. It's atmosphere conditions instead. Oops, I forgot to print the mass flow. Let's just open it again then. Let's see, where is my simulation? Double click this Simulink file. Make sure the file is in our folder. All right, we need to wait for a moment to get a MATLAB, the math laboratory, to start our Simulink playing. Now, let's just run. Pretty good. Let's find out our mass flow to see where is our mass flow. This is expression gamma. Here. This is our ideal as mass flow. So it will be our inlet C conditions. All right, we'll just minimize it in case that we may use it for one more time. So let's back on our Fluent and back to our desktop to find our inlet C. So let's see. The mass flow is 0.8360 2.836 e -5. Remember, it's the unit of this print screen is gram per second, but this is kilogram per second. So we need to times 10 to the -3 power, and our initial gauge pressure is equal to 0.286, and our thermal will be found to be total temperature to be 300 Kelvin. So let's apply it. And our outlet, we'll just double click our outlet to set it as a 1461 Pascal, and thermal will be 79.22. Very well, let's just apply it. And about our wall, the heating chamber remains the heat of we use the temperature conditions to represent our thermal conditions and set our temperature equal to 3.315, thickness of the wall will be 0.2 e negative 4 meters, and just apply it and select our nozzles. We use the radiation models to represent the simple conditions. Our emissions will be 0.34 aluminum materials, and the external radiation temperature will be 79.22, just as the external temperature of the chamber, and our worst thickness will be 0.5 e negative 4, and just apply it. Now let's set our monitors. Residual monitors. It's good habits to take this as 1 negative 6, 1e negative 6, negative 6, negative 6. Right. Let's copy and paste it for every standard of it. Great. Now let's do our initialization, make a standard. And in user-defined models, we need to create some customized field functions to calculate the thrust. The calculus thrust will be an integral over the exit cross section, the cross section area of the exit of the nozzle. So we'll take the integral function. So first is the static pressure minus 1461, which is the exit pressure of the nozzle, plus our momentum flux represented by the density, select, and times the velocity, magnitude, select, to the v squared, this is our integral function of the thrust, and let's say it's thrust. Define it, and you can also manage it to save or load, or you can save it to our folder. If you like, let's say it's thrust. All right, so let's close it. So let's check our report if there are integrals. All right, it's good. So let's back on our initializations. We choose the inlet phase to initialize our conditions. We turn on our coordinate. So everything is good. So let's just initialize it. Wait for a moment. All right, we've done our initializations, and now let's set our number of irritations to 1000 irritations and do our calculations. Oops. Looks the converging speed is a little bit faster than I thought. Here we've done our calculations. We need to wait for a moment. The Fluent always works like this because it's all just stuck at this page, which is really annoying me. Now all we need to do is just wait. Oops, the calculation complete. And now let's look at our results. We may want to create a surface to maybe a plane. Just plane for x, y, which shows the xy plane. Let's create it. So let's see. Now, let's say it is pressure. And we select all of this except this plane. Show it. All right, it's great. The result of the simulation is of high quality. So we can see a bunch of deep blue and deep red and some choke flow in the throat part, just as we thought. So let's close it. And let's say we create a new one. Make a velocity contours. Say, we cannot see clearly throughout the surfaces, so we need to create some XY plane. XY plane contours. We're doing the latter. We'll be doing the later. So let's say the final will be our temperature. Looks pretty good. The reason of choosing radiation as the mode of the heat exchange for our nozzle is that the main the main way of heat exchanging in the vacuum environment is radiation, because there's few air on the vacuum environment for this thruster to work. So the radiation is the main way of heat exchanging. And next, we'll create the temperature of the plane XY. So let's say it's temp XY. So let's display it, which is pretty great here. So let's see. If we right click this point, we can see our we can see the the value of the temperature in this nozzle. So let's create another contours of the velocity to see if our velocity is meets our results. Oops, it's velocity. All right, the final exit velocity is 677 or so, but our desired demanded velocity is 705.3 meters per second, which is a little bit. It indicates that our assumption is so ideal that we need to maybe we need to to adjust our correction factor lambda to redesign our this nozzle. All right, so next is our final one will be our oops. We'll rename it as the XY. Save it. And missing I mispronounced this word. I need to edit it to make it correct. To correct it. It's velocity rather than it's a 9 rather than a U. Alright, final things to do. We create a pressure XY, which is great. Oops. Oops, my wall thickness has too high, raised too high. Oh, that's why it's so strange. We need to calculate a little bit later. The thickness of the wall of the nozzle is equal to 0.5 millimeters. It's really thin, right? But it's just a normal value. We need more time to wait. We need to close our Simulink because the Fluent has taken up too much calculation. Also, I need to close that down. oops, our k epsilon, the value of the k epsilon, the scale residual of the k epsilon has converging for so fast than I thought. All we need to do is just wait. So this page is stuck on. It's just stuck on the on this moment. It's good habit to back up our case and data files when we do the calculation, when we do the CFD simulations, because if we lose any, if the page is stuck on this page, if it's just stuck on this page, we can just um, import our backup case and data files uh, to get back our data, to get back our results, to get back our case, get back our mesh. Maybe just wait for a little bit too long, but we need to be patient. All right, we've done our calculations, and now let's look at the contours. Let's see our, now it's much more, it's much more more normal, much more correct, it's much more suitable, much more rational results. Split this, right? So you can see that the edge, the wall of this nozzle, the temperature of the wall of this nozzle is equal to 323.13763 Kelvin, which is rational. So now finally, let's do some integral, some surface integrals. Integrals custom. Let's do our outlet. Let's compute our thrust, which is equal to 21 21 millinewton, 21 millinewton thrust. The thrust is equal to 21 millimeter, which is very ideal, typically ideal. So let's remain our good habit. Let's just export our case. mesh. This is for Laval thrust. And export our data, which is our Laval thrust. And finally, let's just export our boundary mesh data, which is Laval thrust. Pretty fine. So now we can exit this Fluent now. Right. Let's check our folder to see if the mesh, the data, the case files if it is in our, if they're all in our folder selected. So let's say maybe it's in here. So we can see our thrust, our Laval thrust, our Laval thrust mesh data, our Laval thrust data files, and our case files, which is all saved. Or we need to wait for a moment to get them fully closed down. All we need to do is just wait, and wait. Well, anyway, there's something to be pointed out, which is you can see that the result of the simulation is typically axisymmetric. So there's no need to simulate the whole Laval nozzle, the whole 3D models of the Laval nozzle. We can just create the sketch of the 2D the 2D parent faces of the Laval nozzle and just do simply the simulation of this 2D sketches of the parent face to save our calculation. We no need to. It's typically unnecessary, completely unnecessary to simulate the whole 3D Laval nozzle, which is you can see it's really naughty to shut down. Let's shut out again. If it's failed to shut down, we can. The only thing we can do is just shut down on our backwards. We'll close that again. If it's failed, we'll completely delete this project. But we can build a new one. We can still build a new one. Let's open it and let's save our projects. Let's see our progress of saving. Let's continue being busy here. Maybe I'll shut out this picture. I shut out my IDM downloader. All right. Anyway, my task today has been finished right now. So here's our video.